Hi, I want to continue our discussion on gases by looking at pressure. What are the units, how it's measured, etc. There are three topics that I want to cover. What pressure is and its units, how to think about pressure from the atmosphere, and using instruments like barometers and manometers to measure pressure. Let's take the first one, what pressure is and its units. So pressure is force divided by area, or force per area. P equals force, and then capital A for area. And with that area, it will be most likely meters squared. What about this force? Let's look at another equation that you may be familiar with from physics. Force equals mass times acceleration. Now, this mass is in kilograms, and acceleration has a unit of meters per second squared, and that is equal to a Newton. And the symbol for Newton is big N. Newton. Where did this come from? If you have let's say a mass of 1 kilogram, 1 kg, it is the acceleration to push that mass. And in this case, we'll say acceleration has the units of, well, it's to 1 meter per second squared acceleration. And what am I trying to define? If that is the acceleration, that is the mass, that equals 1 Newton. So 1 Newton equals 1 kilogram dot meter per second squared. And that's the force. So the force is a Newton. And let me write that down. So this is the SI unit for, just double check. Did I say that this was a Newton? Let me just get rid of that. The Newton's actually this down here. For force. So let's put that into this equation here. So pressure has the units of newtons per meter squared. Okay. Next, well, what is this unit of pressure then in total? 1, and we're going to call it Pascal. I'll put it here. 1 PA, so that is a Pascal. That is the unit now of pressure. So this is the SI unit for pressure. And it is equal to 1 Newton per meter squared. Okay, so let's backtrack and let's put some boxes around a couple of these key conversions. If I take it that the SI unit for pressure is 1 or a Pascal, what is a Pascal? A Pascal is 1 Newton per meter squared. And where's that Newton coming from? That Newton's coming from here, which is a SI unit for force. So this is force per area, and this is the SI unit for force. 1 Newton equals 1 kilogram dot meters per second squared. So if we substitute this, I just want to express this in terms that we're a little more familiar with. This is 1. So what's going to cancel out? If we substitute this for that, it's 1 kilogram. This meters cancels out. So on the bottom we have meters dot seconds squared. But if you want anything to, if you really want to focus on the things that you should know or memorize, it's the ones in boxes. Okay, Pascal, and again this is a Newton. And we're going to continue with pressure, so this is the more important of the two. Now, you may not be familiar with Pascal, or you may know other units of pressure. Other units of pressure. We have the PSI, right? Your car tire is measured in PSI, the pressure in the tire, and that for my car is 32 PSI. You may know atmospheres, ATM. We also have millimeters of mercury, mmHg, and that's actually equal to a torr. 1 millimeter mercury pressure equals 1 torr. Okay, that's number 1. What pressure is and its units. It took us a while to get there, a little bit convoluted, but we got to Pascal. Although for most of your problems you'll be converting Pascal or other pressure units into ATM, but that is definitely in a future video, not in this one. Number 2, how to think about pressure from atmosphere, the atmosphere around us. Let's get a person. And that person feels atmosphere, feels pressure on it. So in green, this is the pressure from the atmosphere. Okay. Now, why aren't we being crushed by all this pressure pushing at us? It's because we have an equal pressure exerting away from us. So the pressure in the body counteracts the pressure in the atmosphere. Perfectly balanced, right? Pressure in the body counteracts. We'll call this now the P of the atmosphere, ATM. Just be a little bit careful. This is ATM, the units, atmospheres. This is ATM just in general, the atmospheric pressure. Okay. Now, is this really true? Do we really have gas molecules inside of us pushing against the atmospheric pressure, or against us, the container, that is also feeling pressure from the atmosphere? Well, what if we eliminate gas inside of that container? And in particular, let's use a metal container. And if we apply a vacuum, or we evacuate it and we cap it, so here we now have the same container, but now we took out all the air and we put a little cap on there, or a septum, or something like that. So it's not open to the atmosphere. What's going to happen is it's going to start to collapse on itself. Okay. So it collapses. And then that's because atmosphere is pushing against it. But there is no counteraction. There's no gas inside pushing against the walls of the container inside. It's completely evacuated. So there's no gas molecules inside to push against the walls. Push against the container walls. Okay. Alright. Let's continue. Now let's put numbers to this pressure that is being contributed by the atmosphere all around us. The pressure in or at sea level, let's put here at sea level. Why is that important? Because at sea level you have this theoretical column of air above you. Okay, and that has a mass, or that has weight, pushing downward. At sea level, we're going to start with ATM, I think. At sea level, the pressure equals P equals 1.0, and now this is ATM, that atmosphere unit. Next, that is equal to 760 millimeters of mercury. We'll go over in just a bit why they're using a distance of mercury to relate to pressure. That is the same as torr, though. So actually, this measurement of millimeters of mercury, that was given a name, torr, for the person who developed the instrument, I think the manometer to measure pressure. Okay, next, that is equal to, well, what the heck happened to pascals? Like, pascals is the SI unit. Well, that atmosphere in torr is equal to 101.3 kilopascals. And then what about what we're used to, the units in tire pressure? This is equal to 14.7 psi. Okay, so that's at sea level. Let's go up in elevation. So in Denver, you know that in Denver you have thin air. Okay, it's hard to breathe. The P there equals 0.816 ATM. Okay, so it's less. As you go higher in elevation, the atmospheric pressure drops, and then maybe in PSI, let's do that. That's actually 12 PSI. Okay. So you can see the difference there. Now, the last thing, just a trick, or a really quick thing, to convert, let's go millimeters of mercury to ATM. Just take the millimeters of mercury, and just divide it by 760. And that will give you the pressure in ATM. Alright. You can even go backwards also. So if you want to go to mmHg, just take this ATM, 0.816, and what do we do here? We multiply it by 760. Okay. Okay. The last topic is looking at these instrumentation, barometer and manometer. I admit that as an undergraduate, I did not quite fully grasp what the heck is going on with these instruments and how a simple tube of mercury can tell me what the atmospheric pressure is. Let me see if I could diagram it for us, though. Number 3, we're going to look at first a barometer, or let's say number 3 is instruments. And the first one is a barometer. And actually, this was the one that was invented by Torricelli. Invented by Torricelli. So that's where Tor came from. Has this been focusing? Okay. Here's a schematic. Initially, what you have is an inverted tube filled with mercury, and we're gonna let me give us a level of mercury in the container up to there, and let's give it some high walls. Let's see if this is going to work. So all of this is filled with mercury. There's no air in that tube. It's inverted into a container, a reservoir of mercury. So what's going to happen here is that we're going to see the weight, or not the weight. No, we're right. There's going to be a weight of the mercury in the tube pushing down. This is initially. Once that tube goes into mercury, it's going to feel the weight of the mercury pushing down, and then eventually it's going to go to this situation. It's going to find some equilibrium where it's not going to push out all the mercury. It's just going to push out some of it. And here are our walls. And I want to indicate that this level rose. Because this mercury in the tube is pushing down. Okay, so hopefully you can see that. There's now a pocket here. It has no air. Okay, it's still under vacuum, but the weight of the mercury is forcing some of it out of the tube, and they're going to find a spot where the ATM is pushing here, the atmosphere pressure, is going to equal the pressure of the weight of the mercury inside the tube. And put that right here. Oh, let me spell this out in words. So the mercury level in tube falls till weight of Hg in tube is, and this is the important part, supported by the pressure of the atmosphere pushing back. So really what I should put here is in green. Now this is the weight. It's a little bit hard to see. But the weight of the mercury in the tube is pushing against the weight of the mercury that's being pushed by the atmospheric pressure. It's going to find an equilibrium, and it's going to stay steady. Not the best drawing because the height is not as large as I want it. But they're literally measuring the top of the reservoir to the top of the mercury in the tube, and that is the pressure of the atmosphere. So this is typically to get the pressure of the atmosphere, and if it was at not room temperature, but if it was at sea level, that distance is literally 760 millimeters of mercury, and we know that also as 76 centimeters of mercury, the difference. Alright, so that is the barometer. Manometer is going to measure the pressure of a gas. And the type of manometer that I'm going to diagram is called an open tube type. And this open tube type is to measure gas that has a pressure greater than atmosphere. Greater than atmospheric pressure. So in general it's going to be greater than 1 atm. So again, that is the barometer. Okay, not the best. You could definitely find better cartoons online. Now I'm worried about how I'm going to draw the manometer. So the manometer, there's a bulb of gas, and it's going to swing this way. Typically you have a valve that you could add more gas over here, but we'll make it closed. And this is the important part. You have a U-tube, and the U-tube is going to be open on the, in this case, the right. Okie dokie. We'll have it open here. And again, oh my goodness. Okay, let's stop there. So, mercury again. The mercury here is indicated by the black filled in area. Over here, this gas that I'm going to represent as pink is pushing. It has a pressure, and it's pushing against mercury. So let's say it pushes that far, and it pushes the mercury in the tube maybe this far up. Let's go right there. Okay. So we do have a height difference. That height difference is this. And what does that represent? This represents the P of the gas. Let me put this in pink. Well, no. The P of the gas, pressure of the gas, is equal to the height difference. And in this case, we're using mmHg. So you're using a ruler basically to measure the difference in the height, plus the P of the atmosphere. And again, that is also in millimeters of mercury. Now, does that make sense? It's the addition of this plus the P atmosphere. So if the P atmosphere is like 1.2, and this let's use millimeters of mercury. If the pressure is 780, okay, 780, and the height difference is another 20, then that pressure of the gas is actually 800. So it is more than atmospheric pressure at sea level. Let's use these units actually. That makes sense, because what if the pressures were equal between the gas and the atmosphere? What would you expect? You would expect this. Okay. Still open to the atmosphere. And you would expect this. If the pressures were equal, you expect the heights to be equal. So in this case, you see how the difference in h, heights, is equal to 0? So look at your equation. P of gas equals 0 plus P of the atmosphere. Alright, so you just take the atmospheric measurement using a barometer, and you have now this number here, and then use a manometer to measure the difference, how hard the gas is pushing against the mercury, which is being pushed out again by the atmosphere. But again, if you don't understand this, or if this is a little bit unclear, just remember, well, imagine, what if the gas pressure in the bulb is identical to the pressure being pushed by the atmosphere? Then this height would definitely be identical, and the difference would be 0. In the next video, we are going to start using equations and these numbers for pressure to do some calculations to figure out maybe the volume of the gas, or under certain temperatures, how does the pressure and volume change. We're going to see all of those relationships in the next video.